From this warm-up, somebody tell me how I should set up the equation for Q. Go ahead, Bo. Yes, please, come on up. Yeah, much easier. Oh, sorry. Yeah, yeah. You guys know how much I love this board. Oh, yeah, yeah. Nice, nice. Two thumbs up. Thank you so much, Dr. Sorensen. You're the best. All right, so yes, product times product over reactant times reactant concentration. Nobody has a coefficient, so you didn't have to square anything. Yes, it does proceed forward or to the right. That is the technical term. We talk about it proceeding to the right or proceeding to the left. That is, if it's to the right, it means the forward reaction is dominating. If it's to the left, it means the reverse reaction is dominating. Now, the only thing that is There's one very, very, very small thing that is incorrect about what Bo wrote as his answer. What is that very, very small thing? How many sig figs do we have? Dos, yeah. So. No, you would get the answer right, but you would have, if this was the only time that you had messed up sig figs on paper 2, you would get a point taken off. If you messed up sig figs on every single problem on paper 2, you would get 1 point taken off. So it's not something to stress over, but if you can get it right, why not get it right and save yourself that point? Okay, so we're going to talk about the fun part of equilibrium, and which is Le Chatelier's principle. This is the idea of we're going to go in and F things up, and then we're going to see what happens. Okay, so this is totally a FA-FO situation in the sense of chemistry, right? What do we do where a system is at equilibrium? Everything is just hanging out there, forward reaction, reverse reaction, exactly the same rate. What happens when we throw a wrench in the works? And depending on the wrench that we throw, different things happen. And so this is all about figuring out what is going to happen, predicting what is going to happen after you mess with the system. So the principle basically says, when you have a system at equilibrium and it's subjected to a change, the system will respond to minimize the effect of the change. So it's basically going to try to make up for what just changed. So it's kind of like, I put the word homeostasis on here. That's a biology term where physiology, homeostasis is kind of like maintaining your body temperature, your pH levels, things like that, all within a particular around a particular set point. So, and you can also think of it like a thermostat. So the thermostat in your house, if the temperature gets too high, it turns on the AC to bring it down. If the temperature gets too low, it turns on the heat to bring it up. And your body has a thermostat as well. And it has lots of other systems like that try to keep things within a working range. And that is similar to what is going to happen when we disturb equilibrium. It's not going to go back, your thermostat is set at a certain temperature. If it goes below 72, then it's going to turn on the heat or whatever you have it set at, 68, whatever. And then it'll get it back to that temperature. The system at equilibrium will not go back to the previous equilibrium. but it will go in that direction. It will try to get back towards that previous equilibrium, and we'll end up with a new equilibrium state. Okay, this will make more sense as we go through and look at examples. Okay, so things that we can change that will mess up our equilibrium state. We can dump in some reactants. We can dump in some more products. We can take out some of the reactants or some of the products. Okay, so changing those concentrations is going to disrupt the equilibrium. And same thing, and we have a system of gases, changing the pressure is like changing concentrations, right? If we change the pressure, increase the pressure, concentration of everything goes up, basically. And if we decrease the pressure, concentration of everything goes down, but it's specific to our gases. We'll see some examples of that. If we change the temperature, heat it up, cool it down, that's also going to shift the equilibrium. And if we add a catalyst to the system, so if we had a system that didn't previously have a catalyst in place, and then we dump a catalyst in, we are going to change the position of equilibrium. So these changes can shift the equilibrium to the right, meaning we're going to try to produce more products, or to the left, meaning we're going to try to produce more reactants. And so we want to know what effects are all of these different changes going to have on the position of equilibrium, and how can we work that out? All right, first of all, we'll go ahead with concentration. So this is actually, and I have a video about this, but I'm not going to show it. Maybe I'll show it after exams. The Haber process is a super important process for creating ammonia, which, yes? Yeah. Uh-huh. Yes, that is correct. It is arbitrary, but we arbitrarily decide that what the reactants of the forward reaction are, we're going to keep calling them reactants. And the products of the forward reaction we're going to call the products, even though in the reverse reaction, it's the other way around. It's just for convenience of naming things and keeping those names consistent as we go back and forth. We're just going to keep calling those relative to the forward reaction. Okay, so this is a super important system. And Fritz Haber gets a lot of kudos for figuring out, using essentially Le Chatelier's principles, figuring out how to make this a workable reaction. Because this produces ammonia, which is a way that we get fertilizer out of nitrogen in the air. So plants can do it with nitrogen-fixing bacteria on the roots, but if we want to give them more biologically available nitrogen, we have to put it into some form that they can process. And so this is the base of fertilizer production, and it's the reason that we can mostly feed most of the 7 to 8 billion people in the world today. Now, Haber also, in this process, with playing around with nitrogen compounds, figured out how to make bombs. So he's kind of one of those, like, you know, good, he's kind of good guy, bad guy, kind of both. But in any case, so we talk about this reaction a lot, partly in equilibrium, partly because it's super important. And because it's in equilibrium, because we have gases, there's lots of different ways we can push the reaction to make more ammonia, which is the goal. And so we're going to use this as one of the reactions we look at to try to figure out what the effects are of these different things that we can do to push the equilibrium in one direction or another. All right, so one thing we can do. So we throw in some nitrogen and some hydrogen gas, and we make some ammonia, but at some point we stop making more ammonia. We're always making ammonia, but sometimes that ammonia is decomposing too. So at equilibrium, we're stuck, we're done. We have as much ammonia as we're going to be able to make, unless we pull that ammonia out. So if we selectively remove the ammonia from the system, then we're lowering that concentration. These are not changing. I mean, we haven't done anything to change these. We've just dropped the concentration of ammonia. And so the system is going to react by trying to make more ammonia, by shifting in the forward direction to the right. And you can think about this. I think do I have the, no. you can think about this in terms of Q and K. So like we have a K, okay, and at equilibrium, I'm sorry, Bo, I'm going to get rid of this awful green. So we have a K, Kc, and then we end up with a Q once we've removed the ammonia, or some of the ammonia anyway. Our Q is going to be smaller, right? So our K is our products over our reactants, and our Q is going to be less than the concentration of our products over reactants. So that means our Q is going to be less than K, which means we're going to go to the right. Okay? I'm removing ammonia, the product. And so I'm lowering Q by doing that. And because as soon as I remove this, then it's no longer at equilibrium. So as soon as I remove, we have a particular K, and as soon as I remove the product, it's no longer at equilibrium. Only at equilibrium, yep. Now, we're going to make a new K. We're going to make a new K once we get to a new equilibrium. Okay, it's not going to be the same as the old K. But because we're decreasing this products, we're going to have to make more products, basically. So that's mathematically, but also just intuitively. I take away the ammonia, I still have a bunch of N2 and H2 in there, and so they're going to react to form some more ammonia. It will not come back to exactly the same, because after these two react to make more of this, these concentrations are going to be lower. So the whole equilibrium system is going to change. It's going to shift to a new place, but it's going to shift in the direction of making more product with the reactants that we have left. Yeah. Okay. So that's one thing that we can do in a factory, basically, is we can selectively remove the ammonia, and that will keep the reaction going towards the right, as opposed to pushing backwards. This is on page 14 of your study guide. And this is the kind of graph that you're going to have to learn how to interpret. So let's walk through this graph. Let's walk through this graph together. So we've got time 0, time 10, time 15, okay? Concentration. So this is a reaction in which we have, you know what, I'm going to keep what is going on here. So this is the reaction of interest, right? Which I think is, yeah, it's there below. So we're taking hydrogen and iodine, and we're combining them to make HI. At time 0, the system is already at equilibrium. So we start measuring the concentrations, and the system is at equilibrium. How do we know that it's at equilibrium? Because the concentrations are not changing. There is still both the forward and reverse reaction happening. It is not static, it is dynamic. However, there's no change in the overall concentration. Okay? At time 0, at time 10, what you see is this spike. It happens immediately. Okay? That means that we added that. Okay? We dumped in some H2, some extra H2. All right? And what you see after that spike is how the system responds. Okay? So the system responds by trying to decrease the amount of H2. So the perturbation was added, yes? We add more. Yeah, we add more. We just throw in some more. Stick a valve to our H2 tank and pump some more in. Okay? So we have a certain amount, and then we increase it. So this spike is the sharp increase indicates that we have changed the concentration. We, the experimenters, have changed the concentration. Okay, so look for that. When you're looking at a graph and they don't tell you what happened, if you see a spike like this where it's changing vertically in one direction or the other, it means that we've either added or we've removed some amount of the reactant or product. Okay? So we increased H2. The system, according to Le Chatelier, is going to work such that we decrease the H2 because it's going to go against what we just did. It's going to shift back. So what happens here is the system says, we have more H2. Well, we're going to shift in that direction. We're going to shift to the right, and we're going to make more of our HI. So what happens, the slower changes you see are the responses, both here and in the other two substances. So HI goes up a little bit, the I2 goes down a little bit, and it doesn't have that sharp change because this is what's happening in the reaction in response to the sharp change. Okay, this is the sharp change, and then here's the response in the H2. So now we've reached a new equilibrium. Now everything is steady again. But they're all in different places. Well, the H2 might be about where it was before. That's just, that may not happen. It depends what the relative concentrations were. But you can see that if we now calculate K, we're going to have a different number for K because we have a different equilibrium, and that equilibrium has shifted a little bit to the right so that we're producing more HI. Okay? So you may have a problem where you have a graph like this to interpret, and so being able to recognize when there's a sudden increase or decrease in concentration, that is the perturbation. And then the slower changes are what happens afterwards until we get to the new equilibrium. Okay. Sure. When Q is equal to Kc, that means the system is at equilibrium. So the Q is the measurement of concentration at any given time in the reaction. Okay? Could be right at the beginning, could be partway through, could be at equilibrium. If it's at equilibrium, they're going to be exactly equal because those are the concentrations and they're not changing. So we're at equilibrium, Q is equal to Kc. As soon as we make that disruption, that is no longer the case. So Q is not going to be equal to Kc until the system shifts into its new equilibrium. And then we will have a new Kc, and as soon as those lines flatten out, the Q will then be equal to Kc. So it will be, the Q is at any moment in time. The Kc is at equilibrium, and then again at equilibrium. No, they have to be flat. Concentrations have to be constant to be equilibrium. Okay. Okay, so example 1 on the next page, or the next page, gives you this hydrogen and iodine, the same reaction we were just looking at. So we add extra H2. We actually just saw that in the graph, right? So we're going to shift to the right. Now, what is going to happen to the value of Kc when we do that? So we have a new equilibrium with a new K. So if it helps to look at a graph, the question is, how is this K going to be different from the original K? Okay, so what is the relative number for K? Shane, what do you think? Because we're adding extra H2, it's going to shift to diminish that change that we made. Oh, because we've increased the HI concentration. So this is a lower concentration, shifting to a lower concentration. This is shifting to a lower concentration. This is shifting to a higher concentration. Yeah, so if we're talking about this as the product, then this is shifting up. So what is the value? Is the value of Kc going to be bigger than it was originally or smaller than it was originally? Brendan? Why? You're correct.
I was gonna say maybe like since you're because I did my IA on this.
Uh-huh.
When the concentration of one thing is increased,
Uh-huh.
usually like the rate of reaction gets quicker.
Uh-huh. Yep.
So my thought process was like maybe the higher the concentration of one, the faster that it will reach equilibrium.
That's actually something we're going to talk about in a little bit. How the rate of reaction, rate of reaching equilibrium comes into this. So you're not wrong with all of that, but there's a simpler reason why we can tell from this graph or from the direction that it's going to be increased. Bo? Yeah, that's why. So our products are going up. Now we did spike the H2, but it's going to come back down, and our I2 is also going to go down. So our products are going up. So since it's products over reactants, if we increase the products, then we're going to increase K. So if we're moving to the right, then K is going to get bigger. If we're moving to the left, K is going to get smaller than what it was in the original equilibrium state. Okay. Okay. So if we have a mixture at equilibrium and we add more HI, what's going to happen? Yeah, it's going to shift to the left and the K is going to decrease. Yeah, so just depending, that's what makes concentration relatively easy, is because you can just look at what side is the thing that we changed, in what direction is it changing, and how are we going to move. You just really have to look at the equation to know how that's going to work. Okay, changes in pressure are like changes in concentration. The difference is that pressure only affects substances in the gas phase. That's not to say that we can't have any effects of pressure on something that's in a solid phase, but if you think about it, if I take a bunch of gas and I put it under pressure, I can compress it into a very small cylinder. I can take a room full of gas and put it into a very small cylinder. I can't compress this table a whole lot more than it is already compressed. Okay, so it's the same thing with a liquid. There is a little bit of an effect of pressure on liquid, but it's marginal. And so we're not going to talk about it in this situation, because the effect of pressure on a gas, reactant or product or both, is going to be so much bigger than the effect on any liquid or solid that it basically, the liquid and solid is so negligible we're not even going to consider it. So when we have a container with some gases in it, and we've got this equilibrium system at equilibrium, where one thing is turning into another thing, our reactants are turning into our products, and vice versa. If we increase the pressure, then everything is more tightly packed together. And the system is going to shift to try to compensate for that, to decrease the pressure. Okay? Now, the pressure of a system of gases is dependent on how many moles of gas we have. And so, depending on which side of the reaction has more moles of gas, then we're going to try to shift, if we increase the pressure, we're going to try to shift to the side that has fewer moles of gas to alleviate that increase in pressure. That could be by, if we've done this by decreasing the volume or, dumping more stuff in to increase the pressure. That's kind of conflating concentration and pressure. But basically, I like to think about it usually in the sense of we're making the container smaller or we're making the container bigger. It's just easier to visualize that way. If we decrease the pressure when the system is at equilibrium, it's going to try to compensate by increasing the pressure, by counteracting that decrease. So we're going to shift to the side with more moles of gas. Okay. Here is an example. our wonderful Haber process, N2 and H2 making 2 and H3. So on the left side, we have our nitrogen and our hydrogen total up to 4 moles of gas. On the right side, we've got only 2 moles of ammonia. So if we increase the pressure of the system, the equilibrium is going to shift towards making fewer moles that are going to take up less space in order to alleviate that change in pressure. Okay? So one of the things that we can do in the Haber process is we can remove the ammonia and drive the reaction forward that way. We can also increase the pressure, which is going to drive the reaction forward in this case. So what you have to do when they're talking about pressure is you have to pay attention to what reactants and products are gases, because you do have some reactions where you have like a solid reacting with a gas to make another gas or to make a solid, and then it's only going to depend on gases on one side of the reaction. But then also look at the coefficients, look at the moles, number of moles on each side. All right, so page 15, here is an example reaction. We've got carbon monoxide reacting with hydrogen to make some methanol. I didn't realize you could do that, actually. I wonder if that's a real thing that people do. I've never really looked up how to make methanol. But yeah, so assuming this is our reaction that we're doing, what is going to happen if we increase the pressure? It's going to go to the right or go to the left? It's going to the right, because over here we've got 1 mole of gas, over here we've got 3 moles of gas. Okay, so if we increase the pressure, we're going to the fewer moles. If we decrease the pressure, we're going to more moles of gas. Okay. All right, concentration, pressure, pretty straightforward. It's about how much we have. Temperature. Do we have time? I don't really have time today. If you're here tomorrow, I will show you this demo with the nitrogen oxide equilibrium. Temperature is going to affect the reaction depending on whether it's endothermic or exothermic. And this is where I find it extremely useful to think about heat as either a reactant or a product and write it into the equation. Okay? So if it's an endothermic reaction, heat is a reactant. It's something that has to go into the reaction in order to make the product. If it's an exothermic reaction, then heat is going to be on the product side. We're releasing heat. It's a product of the reaction. Okay? We haven't really talked about heat as a reactant or a product before, but this is a good situation to think about it that way. All right? Because then you can kind of treat heat like concentration. If we're increasing the heat, increasing the temperature, and heat is on the reactant side, it's going to take some of that increase in energy and drive to the right to the product, make more products to try to alleviate that change in temperature. If we cool it down, it's going to drive it in the other direction to try to heat it back up, to generate more heat in the system and its surroundings, in the surroundings. So depending on where the heat is, a reactant or a product, that's going to affect which way the equilibrium shifts. This is a situation, I'm trying to remember if I have an example. I don't. I will find an example. There might be one actually in the practice questions, but I think I had to make another packet last year for that. Yeah, I will post an example of a graph where there's like the concentrations graph that we were looking at earlier, where you can see the effect of a change in temperature. Basically, what's going to happen is you're going to have something like emitting a spike in the change in concentration. There's not going to be an immediate sudden change in concentration. You're just going to see some going up and some going down gradually. And depending if it's a exothermic endothermic reaction, you can determine, or you can use the graph to determine, is this exothermic or endothermic if you have the equation. I'll give you guys an example of that tomorrow. Okay. Okay. I'm going to skip this for right now. Let's look at this question. So we have a reaction where we have a negative delta H. And we want to know what's going to happen when the temperature is decreased. So what does it mean if delta H is negative? Exothermic, yep. All right, so we have an exothermic reaction and we're decreasing the temperature. Which way is the equilibrium going to shift? Brendan? Okay. Where would you put heat in this equation? Would you put it on the reactant side or on the product side? If it's exothermic. Right. So if we decrease the temperature, the system is going to respond by trying to increase the temperature. It's going to increase the temperature by generating heat. So if we decrease the temperature of an exothermic reaction, it's going to shift to the right because we want to make more heat. We've lost heat, and we're going to respond to that by making more heat. Okay? Does that make sense, Brendan? Okay. So this reaction, going in this direction is producing heat. Going in this direction is using up heat. Okay? Yeah. Right. That's what I'm trying to do. But I don't know if a graph would help with this. So if we increase heat, if we bump up the heat, we add heat to the system. Okay? If we bump up the heat, it's like adding a product. It's going to shift the reaction backwards. Because we're adding more heat, the system is going to compensate by using some of that heat to run the backward reaction. Does that make sense? We're adding energy to the system, and the system's like, I'm going to take that energy and I'm going to put it into the bonds by sending the reaction this way. And that is going to decrease the amount of heat energy that we have. Okay, if I add carbon dioxide, which way is the system going to shift? Yep. If we're adding, what we're talking about is we're at equilibrium, and I'm going to spike the CO2. The system is going to shift to make up for that. Yeah, it's going to shift this way. We're going to use up some of that extra Kc or extra CO2 that we just jumped in. Right? So we're going to take, we just added more CO2 than we needed at equilibrium. Equilibrium is going to shift this way to make up for that, to compensate for that, to get rid of some of that extra CO2. Does that make sense, Brendan? If I add carbon monoxide, it's going to shift to the right. because it wants to use up that extra carbon monoxide that I just added. It wants to counteract what I just did. Okay? So if we think of heat as a reactant or a product, we can treat it exactly the same way. So I had a certain amount of heat in the system, and now I've added more. That's like saying I've added more of a product. In order to counteract that, I'm going to shift the reaction so that I use up some of that heat. Because I have extra heat, and I'm going to use it up by shifting to the left. Just the same way that I used up my extra CO2 by shifting to the left. Shane? I know. I'm trying. I find it easier to. Is that the confusion? Because I'm trying to just use this as an example. Okay. So if I increase the heat, I'm going to push it to the left. However, like Shane said, the question is saying, okay, no, we're not increasing the heat. We're actually lowering the temperature, meaning that we are decreasing the heat. That's like taking out a product. That's like removing the ammonia from the Haber process reaction. The system is going to respond by shifting to make more heat. Because we've lost heat, we've removed heat from the system is going to react by making more heat. The way it makes more heat is preferring the forward reaction. Just the same way that if I took out a bunch of CO2, the system would respond by favoring the forward reaction to make more. Okay? So it's always going to go against whatever the perturbation was. It's always going to try to go in the opposite direction of whatever you did to the system. So if the temperature is decreased, we're going to drive the forward reaction, and we're going to, what's going to happen to Casey? If I decrease the temperature. We're driving the reaction this way. Yeah. Because we're increasing the concentration of the products. Right? No, we're increasing the concentration. We're driving it towards the product side. So the perturbation that we made to the heat by decreasing heat as a product, when we talk about the shift of equilibrium and the changing of K, it's going to be what is the reaction to that. So we're not talking about the lowering temperature itself. We're saying how is the system going to respond to that lowering in temperature? And it's always going to respond in the opposite direction. Yeah, okay. We're about to be out of time, so if you have time to look at the exercises on page 16, where again, you're decreasing the temperature, see what you think is going to happen. In those cases, we'll come back to this tomorrow. And I will do the demo, and we'll finish up this topic.